Simple harmonic motion. I'm going to start discussing simple harmonic motion with an example of a pendulum, and I'm going to look at the pendulum's position, its velocity and its acceleration at key positions, and then I'm going to map out that position, velocity and acceleration on a position, velocity and acceleration time graph. Okay, bear with me with that because obviously I'm just freehand drawing a graph, so it's more a case of a sketch. So let's discuss the pendulum. Now, in terms of a pendulum, what we're saying is this is a very simple pendulum. The string has no mass to it. Okay, we're assuming there is no mass to this. So it's a light string. It's inextensible, it's not going to stretch. And then the mass at the end, we're suggesting this is more a case of a point mass. Okay, so all the mass is kind of concentrated at its center. It's not a complex shape, it's just a point mass at the end of this string. Now, if I were to lift the pendulum up, okay, so I was to slightly displace it, okay, so if I put the pendulum in this position, what I've now done from an x coordinate position, so moving it over here to the left, I have moved it a position which I'll call A, the amplitude. That's going to be the maximum displacement of my pendulum. So I'm holding it in position and I'm about to let go, and it'll start to swing back to what we call the mean position. And that means that X is going to be 0. Okay, so 0 displacement when it gets back to the middle. It's then going to carry on and it's going to swing to the right. And at that point, I'm going to say that it's also going to be displaced by an amplitude size, but obviously in the negative direction from the mean position. So it's going back and forth about its mean position to a maximum displacement, which we're calling the amplitude, a positive displacement and a negative displacement. All right, so if I try to draw this graphically, okay, so if I say that this is going to be a position time graph, and I want to know key points in this, and then I'm going to try and join those points up. So to begin with, at the start, okay, this is what I'm going to class as times 0. Okay, so when time is 0, and then this midpoint is 0 displacement, and then obviously going up a positive displacement or a negative displacement. And to begin with, we set this in motion at time t equals 0 at a displacement that we're calling the amplitude. Now, some key features then. This will swing and head back when it does one complete cycle, one oscillation. We'll call that the time taken will be the time period. Okay? So the time period for this pendulum would mean it would get back to maximum amplitude, maximum displacement, positive amplitude. So let's just mark on this graph. When the time is the time equal to the time period, it's going to be back to this position. Now let's look at some other things that's going to happen. Well, when it gets all the way over to here, it's halfway through its cycle. Okay, so the time period at this point, sorry, the time is going to be half the time period. Okay, so that's just roughly half between 0 and the time period. So this is going to be half the time period. We're saying that it's going to be at a maximum negative displacement. Okay, so this is negative there, and so it's going to be here. Okay, now we can look and see how long it would take to get to the mean position. Okay, so as it moves down, okay, this is going to go through a quarter of the time period. So a quarter, half, 3/4, a full time period. So at a quarter and 3/4 of the time period, it's going to cross that midpoint. It's going to be at 0 displacement. Okay, and then what we have then is we've got, if I join these up, try my best. We should have this this shape curve, okay? And this is actually cosine. So this is actually described by cosine of the angle, and then obviously if you did cos of the angle, you'd get a number between 0 and 1, or minus 1. But we have not just 1 or minus 1, we've got the amplitude, okay? So this is going to be, the position of this is going to be described by a cos theta, and then, not to go into any detail, but simple harmonic motion is mapped perfectly to circular motion. And in a circle, so if something's moving around in a circle, the rate at which it moves around, its angular velocity, is going to be equal to the angle it moves through in the time taken to move through that angle. So we can actually replace theta with omega t. Okay, so the position is going to be a cos omega t. Okay, so this shape to its position over time is going to be described by this. Okay. Now let's think about the velocity. Okay, so the velocity of the object, when we start back at time t equals 0, I haven't let go yet, so it should be its velocity. So if we think about mapping on the velocity on this this graph, we've got velocity equals 0 at this point, and likewise as it heads over to here, it was moving in this direction before changing its direction and heading back. So that means it's kind of reached 0 velocity before starting to increase its velocity in the opposite direction. But at that extreme, it's also going to be 0. Okay, so at the t equals time period over a half, over 2, sorry, it's going to be a velocity of 0 as well. Okay. And then likewise, when it gets all the way back to the time period, t equal to the time period, its velocity again is going to be 0. So every time it gets over there and back, every time it's at the extreme position, it's going to have 0 velocity. So there, there, and there. Now when it crosses this midpoint, it should be traveling at maximum velocity. Okay. And again, without going into much details, let's just think about in terms of kinetic energy. It should have its greatest kinetic energy here, so it should be traveling at its fastest before it starts to head back up and lose kinetic energy, so velocity would decrease. So at this point, you're going to get maximum velocity, but we've got to think about direction-wise. So if I've displaced and said that's positive displacement, obviously heading back that way is going to be a negative velocity. So to begin with, as it passes the midpoint here, you're going to have maximum negative velocity. So it's remember, this is the time when it is quarter or 3/4 the time period. So when it's a quarter, you're going to get negative. Not that this is the same scale, okay? Maybe just to make it clear, the velocity might not necessarily be equal in size to the displacement. So here at t over 4, it's going to be minus, okay, so this is our maximum negative velocity. And then when t is 3/4, because it's now heading back in the direction of positive displacement, it's going to be at a positive maximum. Okay, so let's just put there. So we've got this point, this point, this point, this point, and this point to join up. So if not too bad. Okay, there we go. So this is the shape of this graph for velocity time. Okay, now we can get to this shape by differentiating this function, and this is because velocity is equal to dx by dt. So if we differentiate for position with respect to time, we're going to get the velocity. And not turning this into a maths lesson, but what happens is cosine becomes negative sine, okay, omega t, but we also have to differentiate with respects to t, so you pull out omega as a constant, so you would have omega a. So v is equal to minus omega a sine omega t, and that's describing this wave. So just as a little standalone, I'll write it there, minus omega a sine omega t. And finally then, we'll talk about the acceleration of the object. When you've reached your maximum velocity, okay, at that point, your acceleration will be 0, because you're no longer going to be changing your velocity at that point. It's reached its maximum. Once it goes beyond that point, there will be an acceleration, and then it will start to change its velocity. But at that point, 0 acceleration, nothing, no the force now is causing an acceleration to increase your velocity anymore. There will be a restoring force that's going to cause a deceleration in that direction, okay, just after that. But at that point, the acceleration is 0. And then at these extremes, this is when you've got your maximum acceleration. Okay, and this is linked to how far you've displaced it, so how much restoring force there would be. It's at a maximum, so its acceleration is a maximum. It's going to start to change the velocity of the object at the most rate, if that wording makes sense. Right, so acceleration now at the extremes at t and t a half, we've got so let's think so in terms, so let's just make this clear. In terms of displacement, the displacement's positive. However, you are now going to head in an opposite direction, so your velocity is going to be negative, which we've described. To get that motion in that direction, the force acts in that direction, the acceleration is in that direction. So that's then opposite to the sign of this. Okay, so this is a negative maximum acceleration. And likewise, when you get to this maximum negative displacement, your acceleration is now going to take you in this direction. And so that direction was positive. So when I was talking about having maximum acceleration at t equals 0, that means maximum negative. And likewise, when we get to the time period t, we've got maximum negative. Maximum negative. We've gone from t equals 0 to t equals the time period, and we're at maximum negative acceleration. When we get to the halfway point, it's positive, okay, so maximum positive. And then a is 0 at a quarter of the time period and 3/4, so here and here. So we've got this point, this point, this point, this point, this point. Okay, and hopefully you can see the position graph is similar to the acceleration graph. We'll talk about that in a second when I've now mathematically differentiated the velocity with respect to the time to get the acceleration. So at any point on your velocity curve, if you find the gradient of that, it's telling you the acceleration. So for instance, here at maximum velocity, yeah, the gradient would be 0 and the acceleration is 0. Here, obviously, you've got maximum, the gradient's now at a maximum negative, so it's a maximum negative acceleration. Here you've got a maximum gradient but positive direction, so the acceleration's maximum positive. But if we do differentiate this, you would get cos of omega t, bearing in mind that was negative to begin with, so it remains negative, and then pull out an omega because you're differentiating this with respect to t, so you get omega squared a. Okay, and if I just bring this up, put it in a box, omega squared a cos omega t. This is the key thing to notice. Acceleration is equal to minus omega squared a cos omega t, but we know that a cos omega t is the position. So you can combine this equation with this equation to get a equals minus omega squared x. So a equals minus omega squared x. And this is key to simple harmonic motion. This is what simple harmonic motion is. The acceleration is proportional to the displacement in the opposite direction, in the negative direction. Well, negative if that was positive, and then positive if it's negative, but in the opposite direction. And that's what this curve and this curve shows. Okay, so I think in terms of a little bit of theory there, because I'm going to go on to talk about how you work out the time period for a pendulum and also the time period for a mass spring oscillating. But I think the video would become too long if I did all that at once. So we'll leave it at this little bit of theory, and then the next video I'll discuss how to calculate the time period for the pendulum, because there's an equation that we can derive, and also there's an equation we can derive for a mass oscillating on a spring. Okay.